Good morning, everyone. My name is Poom Kumam. I am professor in King Mongkut University of Technology, Thonburi, Bangkok. But, first of all, I would like to thank organizing committee for that conference. Also, Professor Hung is always invite me to join this conference. Many times I visit in Ho Chi Minh City for this conference every year, but in this year, maybe for COVID-19 situation is not good, so we can talk about this conference by online. My topic about is an alternative extracranial method for a vector quasi-equilibrium problem to a vector generalized Nash equilibrium problem. This is my joint work with my candidate PhD student Dr. Premyuda Detbun and Dr. Princhai Panya. But today I am very sorry because I have another meeting and in the same time. So I will record the video presentation by my student, my former student, Premyuda Detbun will present in this video conference. Thank you very much.
Thank you, Professor Poom, for introducing me. So today our talk will be divided to be 3 parts. The first one, introduction. In the introduction, we first consider the notation in this work. Given capital N as the set of finite natural numbers 1, 2, 3 until small n, we consider the convex set xi from the set E, non-empty set E. For all I belong to this set, we denote that we can write x, this x set, as this notation, which means that it is the product of x1, x2, x3 until xn. And this notation x minus I, we understand that it is this notation means xi product x2 products until xi minus 1, and then we skip xi, and then we product xi plus 1 until xn. From this notation, we can see that if we consider x just a point x in this set x, which can be written as x1, x2 until xn, we also can consider x minus I. In this set, this one is x minus I. Sorry for mistake here. So we have that x minus I is the tuple of x1, x2 until xi minus 1. And we skip xi to the xi plus 1 until xn here. So from this notation, we can have that we can write x equal to x minus I and xi. Next, we consider the notation of Nash equilibrium. The concept of Nash equilibrium is no one can gain if other players don't change their strategy. We give you a simple scenario. In this scenario, we can know it as prisoner dilemma. That is, the police has 2 suspects. The first suspect, we call him player 1, and the second suspect, we call him player 2. Both players can select to tell the police, or they can keep quiet. In case that player 1 tell the police and player 2 tell the police, they both will go to the jail for 8 years. And if player 1 keep quiet, but player 2 tell the police, you can see that player 1 will go to the jail for 10 years, but player 2 will be free. From this table, we can write the notation in mathematics. That is, x1 and x2 is the strategy set of both players. Player 1 can select to tell and keep quiet. That is T and Q. And player 2 also can tell or keep quiet. that is set of T and Q. From this value, we will use the function, call it as loss function F1 and F2. F1 is the loss function of player 1 and F2 is the loss function of player 2. Both function is mapped from both strategy set to the real number. As our explanation that if player 1 play tail and player 2 play tail, for loss function of player 1 is 8 for the player 1 and loss function of player 2 is also 8 for player 2. Other value can be observed like this. We can see that to be quiet would be the best outcome for both of them, right? But for the Nash equilibrium, we can observe that arc mean of F1 when player 2 consider to tell the police is to tell. And arc mean of player 1 when player 2 consider to keep quiet is also tell. And for the player 2, arc mean of the player 2 when player 1 consider to tell the police is to tell also. And arc mean of the player 2 when player 1 keep quiet is also true. It's also T for tell the police. From this, we can observe again that arc mean of F1 when player 2 consider to tell the police is tell. In the same way, if player 1 play tell, player 2 can get the loss function that is T, tell police also. From this, we can see that T is the Nash equilibrium, meaning that instead of the keep quiet for both, they are punished for it here because they may shoot telling the police by using Nash equilibrium concept. For the concept of Nash equilibrium, next we consider the real value objective function in the generalized Nash equilibrium problem. Recall that for each I, we define Fi as a loss function which maps from X to the real number, and we consider the set value mapping Ki. The generalized Nash equilibrium problem is to find X such that for each I, Xi belong to Ki X minus I, and Xi is an optimal solution of this minimization problem. In other words, we can write this problem to this form. That is, generalized Nash equilibrium problem is to find X such that Xi belong to Ki X minus I, and Fix less than Fi of X minus I Yi, when Yi is belong to this set. Now we consider the vector objective function of generalized Nash equilibrium problem. That is, we extend the concept of real value of Fi loss function to be the vector value function, that is this one. Therefore, we can see that from the previous definition, this notation is not well defined for this Fi, right? So we let Ci be a closed convex and pointed cone with non-empty interior. We can write the new definition of vector generalized Nash equilibrium. That is to find X such that Xi belong to Ki X minus I, and Fi of X minus I and Yi minus Fix is not belong to this set minus interior of Ci for all Yi in this set. On the other hand, vector quasi-equilibrium problem is the problem that we study. It is to find X such that f of X and Y is not belong to the minus interior of cone C for all Y in the set value mapping Kx, where f is the bifunction. We denote that the set of solution of this problem is this set. In 2019, Professor Chen introduced an alternative extra gradient projection method for quasi-equilibrium problem. We can observe that after line search step, they consider the projection of the half space S1 and S2 and the set X from the initial point X0. This algorithm is kind of interesting. Next, in 2019, Uslem and Mohibi consider Amijo type line search with almost the same projection, but projection is from the WK, where WK is the projection of XK again, meaning that they project 2 times instead of project to the intersection set. From this idea, in this work, we consider the set Kx divided from the product of all Ki and the set C divided from the product of all Ci. And also, we define the function f by the product of all Fi, this term. Therefore, we can see that X bar is a vector generalized Nash equilibrium point if it is also a vector quasi-equilibrium point of F. Next part is preliminaries. In this work, we consider real Banach space E with norm. The topological dual of E is denoted as E star. The duality mapping J divided as this notation, that is, the set of V in E star such that the product of X and V equal to the norm square of X and norm square of V. It's well known that when E is smooth, the duality operator J is single value. If we let E be a smooth Banach space, we can define phi as the distance-like function. It is divided as phi of xy is the norm square of x minus 2 multiplied by product of x and duality mapping J plus the norm of y square. This function is better condition than the square of the metric distance, that is norm of x and y square. It is elementary that this inequality holds. Moreover, in Hilbert spaces, the duality mapping is identity operator. We can have that this distance-like function will be reduced to be just only the metric distance, this one. If we consider a set Metcalfe K in E, we can define the generalized projection onto the set Metcalfe K. That is, we take X using this mapping. We can have that it is a unique X0 from the set Metcalfe K such that the distance line of X0 and X is the infimum value of the set of phi of C and X, where C belongs to the set Metcalfe K. This one is called generalized projection onto the set Metcalfe K. Moreover, when E is a Banach space, this generalized projection is orthogonal projection onto the set Metcalfe K. Now, if we consider set Metcalfe K from the n-dimensional real value, and we associate the following set, the infimum of the set Metcalfe K with respect to cone C, denoted as the set of Y from the closure of Metcalfe K, such that there is no other point C, such that other point C is inferior to the Y, to the point Y. So from this notation, we can give next definition. That is, if consider the function, the vector function G and set Metcalfe K. A point A is called weakly efficient if that point A is belong to the set MATCAL K, and we map A by using mapping G. It belongs to the set of infimum of the set GS again. Therefore, we denote as the argmin of this set is the set of weakly efficient point, and we also observe that argmin of the set of GX is intersection of MATCAL K and inverse of G of infimum of GS here. Next definition is C convex. It is just a convex. It is a mapping such that it's convex with respect to cone C in the sense of using cone C. That is the definition of C convex. Next definition is for a vector value G, we can say that it is C pseudo-monotone whenever we have that G of x, y is belong to this with this, then it holds that G of yx is belong to minus C, minus set of 0. And we can say that G is weakly C pseudo-monotone whenever G of xy is not belong to this set minus interior of C. Then it's hold that G of yx is belong to the minus cone C. Next is the definition of smoothness. A Banach E is said to be smooth if this limit holds. Moreover, it's said to be uniform smooth if the limit is attained uniformly for all x belong to this set, x and y belong to this set. Next, this is definition. Next, F is said to be weakly lower semi-continuous if for any sequence with it is converted weakly to the x bar. It implies that limit infimum of this value is greater than or equal to the fx bar. For the upper case, if for any sequence with it is converted weakly to the x bar, it implies that limit supremum of fxk is less than or equal to the fx bar. Now we consider the set value mapping K here, and we can give the definition that mapping K is weak to strong upper semi-continuous at X if for any sequence Xn converges weakly to X bar and for any sequence Yn belong to set Kxn and that Yn converge to the Y bar. Then we can have that Y bar belong to the set Kx bar. Next, we say that mapping K is weak to strong lower semi-continuous at X if for any sequence Xn converge weakly to X bar and for any Y bar belong to the set Kx bar. Then we can have that there exists a sequence Yn such that Yn belong to the set Kxn and Yn converge strongly to the Y bar. So if K satisfy both of condition, then we can say that K is weak to strong semi-continuous at X. Next part is results. In this work, as I said, we consider a strictly convex smooth and reflexive Banach space, and we consider a natural number M, and we consider a closed convex and pointed cone C with its interior is non-empty, and we denote that E star is the topological dual of E, and we let the duality mapping J, and also we given N, this capital N, as the set of finite number of natural number. And then we consider the closed and convex set xi. From that set E. In our work, we denote that SQEP star is the set of X belonging to the intersection of all X of Kx such that Fxy is not belong to the minus interior cone C for all Y from the union of Kx for all X in X. Then in our work, we assume the following assumption. Assumption 1, Fx dot is convex. Assumption 2, F dot Y is positively weakly upper semi-continuous for all Y. Assumption 3, F is uniformly continuous on bounded sets. Assumption 4, Fxx is equal to 0 for any X in the set E. Assumption 5, F is weakly pseudo-monotone. Assumption 6, Kx is non-empty closed convex subset of X. Assumption 7, K is weak to strong lower semi-continuous on X. Assumption 8, X is belonging to Kx. And assumption 9, this set SQEP star is non-empty. From the previous motivation, Professor Chen and Usem Mohibi give us a motivation about algorithm. So from the algorithm, we can have that we mix both of the algorithms together. The first step, we consider the line search, that is Amijo type line search. And the last part is we consider projection from the intersection set as the Professor Chen idea. So from here, we can have that if we project a point X to the set Hi and then project to the set X again, the point will be here. By the way, if we project on the intersection set, that is the purple area here, the point Xi will be projected to this area. In our work, we use the definition of asymptotically solving sequence, that is the sequence satisfying that for each yk belonging to set kxk, there exists a sequence epsilon k such that norm of epsilon k converges to the 0, and for any k greater than k0, we have that f of xk yk plus epsilon k is not belong to the minus interior cone C. Therefore, we can have the following theorem, that is by our assumption, and we assume that E is uniformly convex and uniformly smooth with non-empty set SV EQP. Then the following result hold. The sequence xk is weak cluster point, has weak cluster point, and all of them solve the vector quasi-equilibrium problem. And we assume that if the problem has the unique solution, then the whole sequence is converged weakly to the solution of that problem. From this theorem, we can have that the following result holds, that is, if we reduce the space to be the Banach, reduce the space to be Hilbert, because the Hilbert space is uniformly and convex space. If a vector value mapping become to just a function that is m is equal to 1, then the vector quasi-equilibrium problem reduced to be just original quasi-equilibrium problem. And the assumption will be reduced also just only to assumption here, and then we can have the same result, which is here. So thank you for your listening.